Alright, we'll move to the next topic, which is called as CMOS technologies. So we have seen how the CMOS fabrication is done, and we have also seen what do you mean by a layout with various examples. We have taken different logic gates, and consecutively we have done with the formation of a stick diagram followed by the layout diagram. So the representation is called as a layout, and this layout, once it is ready, this goes for further fabrication. So this is how it is interrelated. And now we'll go with the CMOS technologies. So in CMOS technologies, we are going to understand how the fabrication is done. Normally, fabrication plants are also called as fabs, which are enormously expensive. Huge investment is required for fabrication plants. Earlier, at a decent cost, the engineers and the physicists, usually it involved nanophysics, that is why physicists were important, and it was at a reasonable price. But now with more and more technology being involved and shrinking in size, it requires around 3 billion, but the investment, and only then the fab unit is ready, which is as big as the size of the football stadium. And for research itself, 2.44 billions of dollars is spent, and that is where VLSI is still booming up. And some companies like TSMC, UMC, Chartered and IBM, they operate on foundry model. So they look for the basics of the fabrication, and they have this, and they sell the space to any of the fabrication companies, and they are renting out their place which has been invested. So we are going with the introduction still, and silicon in its purest form is called as an intrinsic semiconductor, and they have bulk electrical resistance. So since silicon is nothing but a semiconductor which is in between the conductor and the insulator, and the conductivity can be raised by adding the necessary impurity or the necessary dopants. You can add the N type of impurity or the P type of impurity by either considering the pentavalent elements or the trivalent elements. So normally boron is used, which is called as an acceptor because it is trivalent, and donors are the pentavalents which have excess of electrons and they donate, and that is why arsenic and phosphorus belong to group 5. So once you have these components combined with your structure, you form it as N type or P type. And when this combination is brought together, we form a junction, and that is a conducting junction. In other words, it is nothing but your diode. So by arranging junctions in certain physical structures and combining them with wires and insulators, various semiconductor devices can be constructed. And now we are already revolutionized. So by just combining P and N, you have diode. By combining P and P, you have transistor. Two types, NPN and PNP. You have PNPN, you have SCRs, and you have PNP and NPN with the MOS technology. You have CMOS or FETs. So this is how more and more devices can be constructed. So CMOS technologies. What are the CMOS technologies? How exactly we are going with the processing of CMOS? The different steps are broadly explained here. So transistors are formed in the front end of line phase, while wires are built in the back end of line. So first priority is given for the transistors, and then next comes the wiring. So in this section we will be understanding both phases of the manufacturing process. So first one is the wafer formation. So initially we start from the scratch where the wafers are to be created, because that itself, in other words, is the substrate, and on this we go on building the layers, and that is how we get the transistors. So the basic raw material used in CMOS fabs is a wafer or a disc which is of 75 mm to 300 mm diameter and 1 mm thickness. So a minute structure which is of this dimension is considered, and we get the wafers from, again we go deep into the physical properties of physics, where we get this wafers from cylinder ingots, bowls or single crystal silicon, and we get it in the form of a pure molten silicon, and this has to be created in a different method called as Czochralski method, which is the most common method, and impurities are added, and that is how you get the wafer to be p-type or n-type. And the atmosphere is typically helium or argon to prevent the silicon from oxidizing. Since it is silicon, which is the substrate, the moment silicon is exposed to air, the oxygen elements combine and form an oxide. So in order to overcome that, it is not at all been interacting with the, it is not being made to interact with oxygen elements. Therefore, it is combined in a chamber, closed chamber, which is normally filled with helium or argon, light gases. So the molten silicon attaches and then crystallizes. So once the wafer has been created, the next process is called as photolithography. So the name says here as photolithography. So photo is light, very familiar for us. Litho is stone, graphy is graph, which is going to be written. So using light, you are writing on a stone. That is the meaning of photolithography. So using light, we are going to create a structure. So once your wafer is ready, the regions of dopants, that is diffusion, polysilicon, metal and contacts are to be defined. Because since we are already familiar with the fabrication model, we have seen how the CMOS fabrication procedure is done in the well structure, N-well type. So we know what is the importance of mask. Using mask, different dopings and polysilicon, metal and contacts are defined. So in areas where the mask is absent, the implantation can occur. That means the region which is masked will not be permitted to have the implantation or diffusion or polysilicon deposition. The area which is unmasked, which is open, only in that region these things will happen. This patterning is achieved by photolithography. So the primary method for defining areas of interest is by use of photoresist. Photoresist is nothing but a layer which is grown on the wafer, which makes the bottom layer or the beneath layer to resist from photo. So photo will have some impact on the bottom layer, that is avoided by photoresist. So after the initial patterning of photoresist, other barrier layers such as polycrystalline silicon, silicon dioxide or silicon nitride can be used as physical masks. So once this is done, you can have different types of physical masks using silicon nitride or silicon dioxide. In continuation with photolithography, you have an UV light source. So the entire wafer, once it is exposed, you will have the oxide. After the oxide, you have the photoresist layer, and this is exposed to UV rays. What is ultraviolet rays doing? The UV light floods the mask from the backside and passes through the clear sections of the mask. Yes, this is also having a mask layer. The layer which is open, mask layer which is open, only then there is a permission for the UV light or the UV rays to fall on the bottom layer, which is nothing but your wafer. And then developer solvent is used to dissolve the soluble unexposed photoresist. If in case any photoresist material is there, that will be etched out by using a developer solution. Thus you will get insoluble exposed photoresist. So it is possible for us to etch the layer and get a window like structure. So this is called as negative photoresist. A positive resist is initially insoluble, and when exposed to UV becomes soluble. The photomask is commonly called a reticle and is usually smaller than the wafer. So photomask is called as a reticle. Whatever the mask you are using in photolithography, it is called as a reticle. Projection printing is normally used, in which lenses between the reticle and the wafer focuses the pattern on the wafer surface. So we need to send the light in one particular region. Therefore, you will have projection printing. You have to see to it that the lens, aperture, all these things are focused and managed as per the design. Earlier the techniques were contact printing, but now it is projection printing, which is updated. So this is how the photolithography is done. So first step was identifying the wafer and generating a required wafer right from the raw material, which was silicon. And then the next process was photolithography. Next we try to form the well and the channel, because CMOS fabrication is done on a well structure, which is N type or P type or twin well. Therefore we have to understand what is a well first of all. N well, P well, twin well. Next we have one more technology which has not been told to you, which is called as triple well. There is a possibility of 3 wells, and on the 3 wells appropriate transistors are created, and that is one technology. Apart from that, which is silicon on insulator, SOI, silicon on insulator. This is also one technology, how based on how the CMOS transistor is created, but our restriction here is to understand 3 types: N well, P well and twin well, and specifically N well more. So how is the well and the channel formed? In a P well process, NMOS transistors are built in a P well and the PMOS transistor is placed in the N substrate. So this is very much familiar. So PMOS transistor is created on an N substrate. So on an N well you have a P transistor, and on an N substrate you will have a P transistor on N substrate. So P well process optimize the PMOS transistor performance. Improved techniques allowed good PMOS transistors to be fabricated in an N well and excellent NMOS transistors to be fabricated in P-type substrate. Just now as I told you, NMOS is constructed on P substrate, PMOS is constructed on N substrate. In the N well process, each group of PMOS transistors in an N well shares the same body node but is isolated from the bodies of PMOS transistors in different wells. So in an N well process, each group of PMOS transistors in an N well, everybody in the N well are on the same body, which is nothing but the same substrate, but isolated from the bodies of PMOS transistors, which is in different well. Yes, very well understood. Well, everything, all your diffusion, all your 3 terminals, source, drain and gate are associated in one common substrate in either of NMOS or PMOS, because it is in a well structure. Well can be either P-type or N-type. Similarly, on the other well, they respectively. So they are isolated together. They are no way connected. So that is what is the beauty of well structure. Similarly, a twin well process optimizes each transistor types. So in twin well, you will get specifically 2 different types of transistors. If it is only N well, one is inside the well structure, one is outside the well structure. But when we compare the twin well, in 2 different wells, you have 2 different transistors. A third well can be added to create a triple well process. Now I had a discussion on this. The triple well process has emerged. It is new to provide good isolation between analog and digital blocks in mixed signal chips. So this is the recent trend which is not introduced to us in our academics. So this is how it is used in analog and digital blocks. It is also used to isolate high density dynamic memory from logic. Next, so we already know what is latch-up. So unnecessary creation of a transistor junction inside the substrate, that is creating transistors. That is how you have the leakage current or the reverse current flowing inside the substrate, which is not desired. So because of this, there is a variation in the threshold voltage, and as a result the entire functioning of the transistor is disrupted. Therefore, in order to avoid this, we have an epitaxial layer. So epitaxy involves growing a single crystal film on the silicon surface by subjecting the silicon wafer surface to an elevated temperature. What exactly is epitaxial layer? So we have a single crystal film on the silicon surface, and you make the wafer to heat at a high temperature. Then the thin film of this crystal is going to get deposited, and that forms the epitaxy. So epitaxial layer prevents latch-up. Latch-up is not creating, latch-up phenomenon is creating of transistor junctions inside the substrate. So once you have the epitaxial layer, the transistor terminals are broken, and as a result the transistor junction is not created and you don't have transistor effect. We have one step called as chemical vapor deposition. So this is also used. And what is chemical vapor deposition? Heating a chemical to a very high temperature, vapors are created and that is made to deposit. So CVD occurs when the heated gases react in the vicinity of the wafer and produce a product that is deposited on the silicon surface. As the name says, this is the procedure involved in silicon vapor deposition. CVD is also used to lay down thin films of material in CMOS process. So when the atoms impinge on the silicon surface, they form regions with varying doping concentrations. Yes, you have the diffusions. I say you have the P substrate. On the P substrate, you are creating a P well. Is it possible? How do you say that? On a P substrate, you are creating another P substrate. Therefore, this is possible by having different doping concentrations. That is what I mean to say here. It is important to keep the process steps at a very low temperature. And diffusion is done by two procedures, or doping is done by two procedures. One is diffusion and the other one is ion implantation. So diffusion is normally heating the wafer to a very high temperature and putting it inside the furnace. And in that furnace you make these respective gases to be formed, and that is how the gases get deposited into the region which is exposed and not masked. That is diffusion. But in ion implementation, this is very commonly used, which is helping us to create source and drain regions. So that was all about your well and channel. Next we have silicon dioxide. So as I have told you, silicon dioxide is nothing but an insulator, acts as an insulator, and thus the bottom layers are safe. So how do we get silicon dioxide? We know the bottom layer is silicon. The moment it is exposed to air, oxide layer gets deposited. In fact, unlike competing materials, silicon has dominated the industry because it has an easy processable oxide. Fine, we know silicon is dominating. And we have various thicknesses of silicon oxide. You have two types, thin oxide and thick oxide. Thin oxide is 0.1 micrometer thickness and thick oxide is 1 micrometer thickness. So at every layer of fabrication we will be using. The first stage we are using thin ox. In the second stage again we are having oxide, and that becomes your thick oxide. So for the only reason that the bottom layers are protected. So various thicknesses are used, and they conclude that thin oxide is meant for oxides and the other regions where you have voltages given for the source and for the VDD. Normally at the source you are giving ground potential, at the drain you are giving your supply. So at that particular regions or that particular area you are giving voltages. So to give those voltages you need to have appropriately a thicker oxide. As I told you, the thicker oxide dimension is 1 micrometer. I hope I am clear with this topic. So how is oxidation done? It is achieved by heating silicon wafers in an oxidizing atmosphere. So what exactly is the procedure for allowing the oxide to get deposited on silicon? As I told, expose it to air, oxidization happens. But to keep it neat and clean, we have procedures. So those procedures are in three different levels. One is called as wet oxidation. Next you have dry oxidation. Next you have atomic layer deposition. So wet oxidation, oxidizing atmosphere contains water vapor and temperature. Oxidizing you will be making use of water vapor, and the temperature is around 900 to 1000 degrees Celsius. So this is called as pyrogenic oxidation, where you have 2:1 mixture of hydrogen and oxygen, and this is called as H2O, hydrogen and oxygen, 2:1, which is nothing but water. So you have water, and from that water the vapor is got, and that vapor which is got only when you heat it to a very high temperature. So this type of oxidation is called as wet oxidation. So the oxygen element present in the water vapor reacts, and that is how the oxide is formed. So this is a rapid process. Next we have dry oxidation. Here dry oxidation means instead of water vapor it is oxygen, and the temperature is much higher than the earlier ones. It is 1200 degrees Celsius. So better quality of oxide is got than the previous. So wet oxidation is comparatively not that good or effective than the dry oxidation. So this is used for highly controlled gate oxides. So normally for gate oxides we have dry oxidation, and wet oxide is used for thick field oxides. So thick field oxide means thick oxide. So what is thick oxide? Where you are giving your voltages, that is to the source and the drain. Whereas for your gate we will be using thin oxide, which is got by dry oxide. Next, atomic layer deposition. When a chemical layer is attached to a surface and then a chemical is introduced, a thin layer of the required layer is generated. That itself is what we will be considering here. That is called as atomic layer deposition. This is also used in the process of oxidation.